Okay, thanks, Ranjini. Yeah, so, and I don't know whether I should thank the organizers, other organizers, for pulling me into this. And I'm really also proud to be part of this meeting because it's a special occasion, as I told you. Giorgio was one of my postdoc mentors. And on that occasion, it's really a pleasure for me to discuss some of the works that were, well, I did certain aspects of the work, and also Giorgio played an inspirational role in this. So Swap Monte Carlo is one such, and the kind of impact it has in the current day's understanding of structural glasses is something which I'm going to talk about in this work. So Srikanth already gave a full introduction to the glass phenomenology, but just for those who are who has missed some of these things. So I'm going to give a one slide introduction to the essential thing which I need. So glasses are liquids which you generally get if you cool fast enough. And nowadays there are glasses where you don't have to cool very fast, but they are complex systems where finding the crystal state is very, very difficult. So getting a glass is kind of an eventuality, and finding a crystal is a bigger problem, and sometimes it's an art. So, so one of the biggest issue about or the challenges in glass problem is that as you cool or increase density, you know, the temperature and density can be two parameters by which you can get the supercooled liquid leading to glasses. The relaxation time or the viscosity, which Srikanth already discussed, grows very, very fast, actually very rapidly. And depending on the kind of nature of the growth, you have two broad classes of glasses, so something called a strong liquid versus fragile liquid. For strong liquid, viscosity grows linearly if you plot logarithm of viscosity as a function of inverse temperature, following Arrhenius type behavior, telling you that the typical energy barrier that the system has to overcome are probably not changing very significantly with the changing temperature. And there is another set of another class of glass forming liquids where viscosity changes very, very rapidly, actually. For example, like OTP, orthotarphenyl, which belongs to this lower end of it. And there, in the low temperature part, the viscosity grows very rapidly. And sometimes this growth can be extremely large. For example, over a change of temperature roughly 50 degrees, viscosity can change by 10 to the 10, 12. And, and this enormous change is something which is a puzzle to many, because if you look at the corresponding structures, for example, if you look at the typical pair correlation function that you can obtain via various scattering experiments, it doesn't change. For example, this one, where selenium is cooled to low temperature, viscosity must have viscosity actually rise from by factor of 10 to the 13. But then you see the G of R more or less look very similar. So, so this is one of the puzzles that the glass community is facing for the last maybe 50, 60 years. And this is the reason why it's one of the unsolved problem. And so main difficulty is like accessing the low temperature part of the glass phase. And and then these are the main bottlenecks. And so I'm going to come and discuss about what are the recent developments that happened, at least in terms of numerical simulations, where this slow dynamics can be overcome to reach to the very low temperature phase of the glasses, and or sometimes of the very high density phase of the glasses. Okay. And so glasses are, in fact, everywhere in our life. So it's not that this is a theorist imagination that they are working on something useless quantity, but this is there everywhere. So metallic glasses are used in all aspects of our life. And then paint, chocolate, and colloid, emulsions, and ketchup, everything belongs to the same disordered glassy things. So understanding the dynamical as well as mechanical and rheological problems are very important to develop important products and also materials. For example, if you go to small scale, this nano scale amorphous solids are becoming very, very important nowadays. For example, nanomoulding using metallic glass. These amorphous metals are called metallic glasses, are of huge importance because of industrial applications. This has already been used for many years, you see, and then So the main advantage is that when you take this liquid metallic glasses and pour into molds, and then when it becomes solidifies, then the changes in density is almost negligible. So that's why when you get the final product, there is not much difference in the structure, and you don't need to do further polishing of the material or the product. Also, these things are of huge use for, let's say, even in micro fuel cells, because nowadays you can actually develop many micro pillars which will have a huge amount of surface, and they can act as a very good catalyst. So this kind of glass amorphous solids are of huge importance for our all practical purpose. So that's why this is the reason why this study of glass phase and as well as the mechanical properties are one of the pioneering directions in the recent days of statistical mechanics and material science. So the other aspect of glass is that sometimes these materials can be even stronger than steel. But the problem is that they actually fail very catastrophically, and this failure mechanism is what is known as the yielding transition. And understanding the physics of yielding transition will also be very important, both theoretically and in terms of other microscopic understanding, so that we can actually come up with the protocols to stop it and or actually delay it. So some of these things I'm talking about because the next part of the talk will be focusing on the physics of glass formations and yielding transition, where the Swap Monte Carlo, a smart Monte Carlo method that was developed primarily by Giorgio and his collaborators, played an essential role. Okay, so let me quickly tell you why these problems are so difficult to understand, because in crystals, defects are very easy to characterize, and when you deform them, or plasticity in crystal can be understood mostly via how defect moves under applied shear. But when you look at the disordered solid, then finding out or defining even a defect is a huge problem. And so the question is, what is the carrier of plasticity in glassy solids? So nowadays, with recent understanding, mostly came from microscopic simulations, is that there are this local plastic event, which looks like a quadrupole kind of a structure. And it came thanks to SLB's solutions, and which matches exactly with this kind of defects. So this is believed to be the soft zones or equivalent of defects in disordered solids, and they may be the primary carriers of plasticity in glasses or amorphous solids. But the question is, unless you know, have the detailed microscopic picture of these solids, there is almost nearly impossible to develop further understanding. So this is the reason microscopic simulations are playing an important role in understanding some of this, the physics of these disordered solids, including colloidal glass experiments. And in the next couple of slides, I'm going to come to some of this one by one. So let me quickly summarize. The main bottleneck is that the glass form, when you do experiments with molecular glasses, then you can get viscosity change of something like from 10 to the minus 4 to 10 to the 12, which is roughly 10 to the 16 orders of magnitude over a change of 100 degree centigrade or Kelvin change in temperature. But in experiment, the microscopic details are missing because it's nearly impossible to image motion of each atoms. So people there are a lot of progress made in colloidal glass experiment, because colloidal glasses are something which you can image via confocal microscopy, and you can actually look at the evolution of individual particles. But the problem becomes that colloidal glasses, the viscosity range that you can access in experiment is typically 4 orders of magnitude. So which is very similar to in silico simulation of model glass forming liquid. There also we have the full microscopic information, but the viscosity range is only very small, 10 to the 4 compared to 10 to the 16 in molecular glass experiments. So to have a better understanding as well as to have microscopic detail, one needs better simulation methods or experimental protocol via which you can actually get at least a fair degree of microscopic details to get a microscopic understanding or to establish a mechanism. And so in this talk, my primary focus will be to talk about the development happened in simulation methodologies, namely the Monte Carlo methods. And so before we understand, go into the sophisticated Monte Carlo methods, one of them Enzo already talked about, this parallel tempering or Replica explained Monte Carlo method, which Enzo and Giorgio played an important role. So let me quickly tell you, this is for a non-expert, for the students primarily. So basically, Monte Carlo is nothing but you just take a system of particles, and then you randomly choose a particle and choose a random direction to displace. And so then you compute energies between your initial configuration and the next final configuration after moving this, doing a random move of a random particle. And then you accept that move depending with this metropolis criteria. And the protocol is like that. You choose a random particle, you draw 4 random numbers between 0 and 1 and generate a random move, which is given by this delta R. And the delta is an adjustable parameter. You tune it such that your acceptance probability is around 50%. And then you accept this next move according to this metropolis algorithm given by this. So in this cartoon, what I'm showing you that by shaded area, it's actually telling you that one random particle is chosen. And then all of these steps are been checked. And whenever the moves are accepted by metropolis criteria, then I move that particle. So this is what is a simple Monte Carlo method. And but the problem is that using this method, you can only access to reasonable degree of supercooling in model glass forming liquid. And you cannot access deep glassy phase because equilibration time become extremely large. And for example, to give you an idea, is if you take a typical system of few thousand particles and do these Monte Carlo simulations of glass forming liquid, then to typically get relaxation time order of 10 to the 4 or 5 picoseconds, you really need to run in your computer for roughly 2 weeks in real time. So now you can imagine changing another decade of relaxation time, you have to run for 20 weeks, which is nearly impossible with the current computation abilities. So this is where enhanced sampling methods are essential, and this is exactly what I'm going to talk about. So I'm not going to talk about parallel tempering Monte Carlo because Enzo already discussed it. So I will skip that slide, and I will directly go into Swap Monte Carlo method. So this is the parallel tempering Monte Carlo, which I'm skipping, and any interested people, audience should read this paper of Enzo and Giorgio from 1992 EPL paper. And just to tell you that this parallel tempering method actually played a very important role in many simulations, including protein folding, and in biomolecular simulation, this is routinely being used as a method to accelerate equilibration process. Okay, so now let's quickly move on to Swap Monte Carlo. So Swap Monte Carlo actually was first was done by Di Gazzillo and Pastor in this 1989 in the context of understanding liquid gas phase transitions. So there they studied this, they incorporated this Swap Monte Carlo moves. But further detail was not given, probably because in the low density limit, this Swap Monte Carlo doesn't play that much of an important role. And this is where when Giorgio in 2001 and his student Thomas Briguera picked up this and proposed and used this Monte Carlo method for glass forming liquids. So this is the paper in Physical Review E. So the idea is that this is very similar to the Monte Carlo method that they discussed, but so you add another step. So this step is, so as usual, while choosing a random particle, you either displace it and then accept that move by some metropolis algorithm, or you choose an opposite different type of particle and swap their position. So if you look at this cartoon, then these two particles are chosen which are opposite in color. So they are basically telling that they are different types of particle. And then you swap their diameter or their identity or their positions. Any of these, they are all equivalent moves. And then you accept this move according to similar the Metropolis algorithm. And this step you continue to do. So just this extra step of particle size, particle swapping actually dramatically improves the relaxation process in this system. And so far, so in this paper, they were able to show that the relaxation process can be can be enhanced by many orders. And so the model that they looked at was a binary glass forming liquids, but because of the particle size ratio wasn't very big, so this glass forming liquid actually was very prone to crystallization. And then it is actually, if you look at this cartoon carefully, now let's say imagine that you have different types of particles, so let's say binary in one occasion, and then you have a large and a small particle. And you are in a very dense scenario. So now if you try to swap this large and a small particle and their positions or their diameter, then it should be immediately clear to you that that these moves will be the acceptance rate will be very low, because any such move will be very costly in terms of energy. And this was exactly the reason why for most of the binary glass forming liquids, this swap Monte Carlo did not have any effect unless you take a glass forming liquid where the particle size difference are not very large. But they have this disadvantage that they are very prone to crystallization. So after this 2001, there was some other improvement that was done by Fernandez, Martin Mayer, and Verrocchio. So where they try to understand why the swap moves in binary glass forming liquids are so low and can it be enhanced. So what they came up with is something called local swap Monte Carlo moves, which they claim that at low temperature, it actually enhances the acceptance rate of this particle swap of two different types of particles by at least a factor of 10. And this is definitely a notable improvement. So just to understand, so their protocol is that instead of choosing any two random particles of different types, choose particles which are within some neighborhood of certain distance. And so this has been depicted in this cartoon. Let's say this is a central particle. You choose this radius, which is given by this dotted circle. And you want to exchange this open circle particles with a filled circle particle, the black particles. And then they are within a neighborhood of area. So then the swap acceptance are generally larger compared to if you do non-local swap. But then one has to also keep in mind that the detail balance has to be maintained, and then the corresponding acceptance rate has to be modified. And this new acceptance rate also take care of how many swappable particles you have in the neighborhood. Okay, so once you take that factor into account, then you have again an equilibrium, an ergodic move that you can do and do a local swap. And this is the paper, this is the work, this is the figure that I've taken from the same set of authors and published in PRE in 2006. There they showed that if you put this system at a temperature close to the mode coupling transition temperature, then the standard Monte Carlo versus local swap has a speed up of roughly 10 to the 3, which is quite significant. And one expects that at much lower temperature, maybe this will be even better. But for strain, for somewhat unknown reasons in some sense, because local swap seems to be working, but it wasn't picked up in the subsequent years. Only this method was used in 2008 to compute the static length scale, which is one of the point of discussion in this meeting, and I'm going to come to that. But the swap Monte Carlo for many years was somewhat in a dormant mode. and it wasn't been looked at the rate at which it has been looked at now. So the story that I'm going to tell to you is related to this massive explosion of research done by people in the current days using SWAP, and the kind of results that people have obtained in the recent days. So just to list some of the major achievements using this Swap Monte Carlo, is this the first thing that I'm going to talk is this robust estimation of static length scale using point-to-set method in a cavity geometry. And this is where it is very important that Swap Monte Carlo moves are taken. Otherwise, one will not be able to equilibrate the system. And the second one is the massive speed up in equilibration process. Once you go beyond binary systems, this is ternary glass forming liquid that some of us looked at. And then subsequent years, then polydisperse Hart-Spear system was looked at by Ludovic Barthier and Daniel Kozlovich and the company. And they looked at the jamming transition and the glass transition in the polydisperse Hart-Spear systems. Also, the same group looked at supercooled liquid in 3 dimensions and reached glass states, which are not even reachable by conventional experiments. And they also resolved one of the major, also achieved one of the major achievement, major goal of understanding glass transition in this kind of soft sphere systems in 2 dimensions. And the conclusion was that the glass transition can only happen at 0 temperature. And so there are also, so this Swap Monte Carlo actually also helped understand some of the physics of ultra-stable glasses, which I'm going to talk about a little bit if there is enough time. And lastly, I will also talk about the mechanical properties, mainly the yielding transition and the shear band formation in these order solids, which are now accessible in computer simulations thanks to Swap Monte Carlo methods. So the next half an hour of this talk will be primarily to tell you where Swap Monte Carlo played an important role and what are the goals that we achieved in this last 15 years, roughly. So the first one is to identify a thermodynamic signature of growing amorphous order in glass forming liquids. So this is important because there are many glass theories. In particular, there is theory of random first order transition, which tells us that the glass transition is a thermodynamic transition, and it is associated with a growth of a static length scale. But this the issue was debated for years after years without any resolution. And eventually, there's a set of people who looked at and computed this thermodynamic length scale or the static length scale via this method called point-to-set correlation function. So the idea is that you take an equilibrium configuration of the glass of the liquid phase, and then choose a small volume of a typical size, let's say R, capital R. And outside that spherical volume, you freeze all the particles, which is denoted by this red spheres here. And only the inside of this cavity or the spheres, the particles which are denoted in the green by green color here, so they are allowed to do normal dynamics. So now you can imagine that because of this frozen boundary, which are denoted by these red circles, so this inner particles will have slowed very largely, hugely slowed down dynamics. And to get an equilibrium quantity measured in this cavity, one needs to have a smart algorithm to actually equilibrate the sample. And this is what where the Swap Monte Carlo was used successfully, but and this is done in this Nature Physics paper of 2008. So but again, this was done for the same binary model glass forming system where the particle size ratio is not large, but still, nevertheless, they were able to convincingly show that if you compute the correlation of these green particles in one of the central region, over a very long time scale, then you find out there is a static correlation which is building up, and this correlation becomes very small if the cavity size is large, and it is significantly large if the cavity size is small. And this crossover length scale is identified as the signature of the growing static correlation in glass forming liquids. And this was shown in the same paper that as you go to lower and lower temperature, this correlation length, which is known as point to state correlation length, actually grows significantly. And this is probably one of the first signature of static correlation supporting the theories like random first order transitions and Adam Gibbs-like pictures that Srikanth talked about a little bit. And so then this was in the year of 2012 when I was the postdoc with Giorgio, and I was in one occasion I was discussing with him about this Swap Monte Carlo because of the work we did, we wanted to use it. And Giorgio suggested to me that instead of binary, try ternary particle or polydisperse particle. And in a dense polydisperse system or a ternary glass forming liquid, the swap move will have very significant effect. And he was more or less sure that it's going to lead to a massive speed up in dynamics. And so unfortunately, at the same time, I actually came back to India and took up this position in TIFR and could not work on this. And in the subsequent year, I was visiting Weizmann, and in an occasion, I was discussing with Itamar, and then this idea again resurfaced, and then we took it up along with Itamar's group and did the Swap Monte Carlo for the ternary glass forming systems. And so as I discussed to you that if you have a very large and a very small particle, then in a dense liquid, swapping them will be very, very difficult. But if you have now one more intermediate size particle, then you can have swap between small and the medium and the large. So this will be a two-step swap movement. And then there will be some increase in swap acceptance rate. And this is indeed what happened. And this is the work which appeared in Europhysics later. And we are able to show that, so if you look at this energy versus temperature data, so the circle, the data denoted by this symbol circle is falls out of equilibrium at a temperature already at 0.2627. But then using Swap Monte Carlo moves, you can actually equilibrate the sample system to almost up to 0.22. And if you and that is already telling us that the swap moves are working, and indeed one is able to achieve some degree of equilibration. So the one of the major problem to us that we had to face was that how do you prove that the equilibrium is reached, and this is something which we had not a very good idea about it, and then we used the histogram reweighting method to find out whether the low temperature data that we have, whether they are reasonably equilibrated or not. So the idea is that in equilibrium, if you have a distribution of your energies, the potential energy at a various temperature, then you should be able to recompute the distribution of this potential energy at a given temperature using all other temperatures. So this is if you are in equilibrium, this is the histogram reweighting method, and then we tried it, and it is not completely certain to us whether this is the foolproof method. But what we realized, what we found, that if you for the temperature T equal to 0.2, this is a reduced temperature, this histogram reweighting doesn't work that well. And so we concluded that up to 0.22, we are probably in reasonable equilibria. So now, and then we also computed the specific heat and try to find out whether that is via two methods, one from fluctuation and one from taking the derivative of energy with respect to temperature. And these are the kind of criteria we used to ascertain the equilibrium reached. And in this case, the other problem that we had in front of us was how do you now compute the relaxation time? So because of the swap move, these are unphysical. So you do not have the timestamp. So you do no longer know how much time you have spent for the equilibration process. And what is the actual relaxation time without the swap move? So this is, then we thought of computing static quantities, for example, the correlation length, static correlation length, via a method which is accessible in this kind of scenario, and try to infer from that. So I'm not saying that this was one of the best way to estimate the time scale, but other methods are also not very well suitable, because on the other cases you have to extrapolate. For example, if you try to use various functional fitting form of the, if you fit your data via various available functions and try to extrapolate to low temperature, then it's also uncontrolled. And I'm going to show some of the data in the subsequent slides. So what we then used, so this is the idea that we had, and we published it in 2012, to compute the same static correlation length by looking at the Hessian matrix or the dynamical matrix in the inherent structure computed at that temperature, and then look at the lowest eigenvalue. Okay, so in this 2012 paper with Idan and Itamar, we propose that if you look at the lowest eigenvalue and do a finite size scaling analysis of that, then you should be able to estimate a correlation length. And then there are other works where we were able to show that this correlation length and the point-to-state length scale actually match very well in the studied temperature window. So then we say that, okay, so this is the method that we are going to use because this is the method which does not depend on any dynamical quantity. So if you generate your configurations at low temperature, then you can go to minimize it and go to the inherent structures and then compute the eigenvalue and then do it for various system size and do a finite size scaling analysis. So this is the raw data, and this is the scaling collapse by choosing an appropriate length scale. So what we found that the length scale within this accessible window of temperature where you can actually equilibrate reasonably with some confidence, the relaxation time or the static length scale actually grew by a factor of 5 or more. So this was very encouraging because in general, the static length scale in the simulation or even in colloidal experiment grows by maybe a factor of 2. That's what also Francesco was telling us. But this Swap Monte Carlo method gave us an extra hand to go too deep into low temperature phase and then estimate the correlation length via this method. And then we assume that this length scale is going to be same as a point-to-state length scale, because I'm saying assume because we have confidence in the high temperature window. In the low temperature window, point-to-state length scale will be very difficult to compute, again because of various equilibration process. And now think of doing this cavity calculation with a frozen boundary. So relaxation time will be even more large. And I think even swap will not be very practical in those scenarios. So given this length scale data, then we try to estimate what will be the typical relaxation time in this low temperature part that we are able to go into because of the swap move. And so note this red circles are the data obtained from molecular dynamic simulations with where the relaxation time grows from by factor of by 10 to the 5, from 1 to 10 to the 5. And so this the data then if you extrapolate using this well-known Vogel-Fulcher-Taman formula, then you get this solid black line, which tells you that in this low temperature phase, the relaxation time would have been huge. So I think this is a wrong estimate of it. But then we also tried many other different functional form, and one of them gives you an estimate of roughly 10 to the 10. And then we used the length scale. And we assume that the length scale and relaxation times are related by this exponential relation. So tau goes as exponential A xi by kBt. So we obtained A by fitting the high temperature part of the data where we have very high confidence about the relaxation time itself because they're obtained from molecular dynamic simulations. And then using the same fit parameter A, we just used obtained the length scale. And these are the symbols that we, the data with the symbols is a rough estimate of the relaxation time. So it tells us that probably the relaxation time is order of 10 to the 15. So nevertheless, even if these numbers are not 10 to the 15, but we clearly see that via swap move, we probably have accelerated the dynamics by at least 10 to the 5 or more. And so this was one of the big step in this in the directions, which tells us that swap moves becomes really impressive and acceptance rate becomes large enough that equilibration for multi-species glass forming liquid, it can do a wonder in equilibration process. And this is indeed what happened, and it led to a flurry of works, mostly in the group of Ludovic Barcia, Daniel Kozlovich, Andrea Ninarello, and Ozawa, and all of these people. So they looked at in 2016 the jamming diagram of hard sphere glasses for a polydisperse hard sphere glass. So they were it's quite intuitive to understand that the swap should work to its best if you do it in the polydisperse and you tune the degree of polydispersity. So it's also interesting to see whether the local swap actually can improve even better than this, but that's probably the future thing one should look at. But even with just normal swap Monte Carlo, this non-local swap, people are able to show that this hard sphere system can be so the equilibrium behavior of this hard sphere system can be obtained even below to the jamming density. So so just for everybody to understand that the jamming phi j, this is the density where if you do it using normal simulation, the relaxation time becomes extremely large, and it's nearly impossible to access dynamically this phi j equilibrium configurations in phi j. But via the swap process, they're able to equilibrate, and they are able to look at the equation of state until to a density which is much below phi j. And so this is the text that was that I copied from this paper. And this is the conclusion. It says that in the conclusion, we presented numerical measurement of the fluid equation of state, the ZCS, of hard spheres in a part of the phase diagram that has thus far been inaccessible to both numerical simulations and in experiments. Okay, so experiment is colloidal hard sphere-like colloidal systems. Our results rule out the possibility that the jamming transition represents the end point of the fluid equation of state, and it suggests that a glass transition, if it exists, is logically disconnected from the jamming transition. So this is one of the concrete example where now people are trying to get an idea that probably jamming and the jamming transition and the glass transition probably are disconnected. And in subsequent years, they looked at now soft sphere systems. And so there, the speed up that they are obtained is actually immense. So for example, if this is a Lennard-Jones type glass forming liquids, and they obtain the relaxation time via swap moves. This is the normal relaxation time. If you just do usual swap and assume that the swap time series is your actual time series, okay? And the actual without swap, the standard Monte Carlo time scale is represented by this gray or the black gray circles. And so typically, the typical pressure that one can, or the density that one can reach is stops here, where the relaxation time is 10 to the 5. But now using swap, one can reach two densities or the pressure, which is much higher, and the relaxation time exceeds 10 to the 13. So here there is probably more than 10 to the 15 or 16. And in typical experiment, one stops saying that, oh, I cannot, no longer can do experiment beyond this, where the relaxation time typically becomes 10 to the 13 or 14. And now you see that using swap, you can get access to the low temperature phase, which is now even not accessible using experiments. So this gave us a huge advantage to understand the deep and an ultra stable glass phase and possible structure of them. So this in the same work, they also looked at computed the configurational entropy, and were able to show that indeed the configurational entropy decreases very, very rapidly, and signals, if you extrapolate still, to a finite temperature to a point where the configurational entropy seems to be vanishing. So the physics of ideal glass transition still remains a puzzle, at least in three-dimensional systems. But now we can actually reach to the glass phase or the structure which are very, very deep into the glass phase, which in the experiment, if you want to achieve them, probably you have to wait 1,000 years, okay, or even more. And so based on this success, they went on to do look at the glass transition in two-dimensional systems. And this is important to know, highlight that due to Marmin-Wagner theorem, it's known that one cannot have long-range order, crystalline order in two-dimensional systems. So the question was, can one have a glass transition in 2D and a finite temperature? And again, due to swap, and this time swap moved. If I quote the number given in this paper, the speed up compared to the conventional simulation is 10 to the 47, which is an astronomically large number. And so as I said, that even if you don't believe those numbers, the speed up is impressive, and one can reach relaxation time which are extremely large. And if you compute the configurational entropy, which tells you how many accessible states you have to explore in the given temperature, then it seems to suggest that this configurational entropy will be vanishing at a temperature T equal to 0. And these people were able to then claim that in 2D glass transition, if it is there, it can only happen at 0 temperature. Okay, so this in some of this title of this paper, it says that breaking the glass ceiling. That means this is the speed up which is achieved, which is unbelievable. And it is beyond even an experiment. So this is all thanks to swap and the algorithm that Giorgio and Thomas Brigger played an important role. And in this occasion, I am highlighting some of this because it tells you that the works of Giorgio actually inspired and influenced a lot of researchers, future researchers, and led to very, very interesting directions as well. And now understanding this was a dynamical part of structural glasses. So this Swap Monte Carlo also gave us hands to understand glasses which are annealed or stabilized to the degree of an experimentally realizable glass, or even sometimes more. So these are extremely well annealed glass, and their properties should be comparable to the experimentally accessible, experimentally tested glasses. So, so in this work, what has been looked at is the yielding transition in this glass forming liquid, which are cooled. First one is via normal simulation method, and then via Swap Monte Carlo method in the moderately annealed glass, and the oil annealed glass is the product of Swap Monte Carlo method. So I'm going to run these videos. For the poured annealed glass, you see this, the colors are the places where you are basically indicating by this parameter called non-affine displacement, the places where particles are rearranging in some sort of irreversible manner. So these are the places which are which we call as plastically rearranged particles. So the green particles are basically plastically rearranged or deformed particles. And you see that for poured annealed glass, plasticity seems to be happening everywhere. And so this annealing or this yielding process is often quoted as ductile-like annealing. So now you generate the glasses which are moderately annealed, and then you see a very different type of behavior. And you see that, there is not much plasticity suddenly until you see a large kind of region where the strain gets localized. And this is an indicator of your shear band formations. So now, so if you look at the extremely well annealed glass obtained via Swap Monte Carlo, then the physics become even, or the phenomena becomes even clear. And you see that until the shear band formation, there is almost no plastic event. And then suddenly there is a slip. And this is exactly what happens in our real glasses. When you look at real glasses or window glasses, and we hit it with maybe a hammer, and then it shatters. So shatters because it forms cracks, and cracks are manifestation of these shear bands. So now, so this shear band formation in this kind of clear format wasn't there with us. to understand the microscopic details of shear band formations. And thanks to Swap Monte Carlo, now we can go and understand it. And if we understand, maybe in future we'll be able to actually stop this shear band formation, and that can lead to better design of glasses. Okay. Yeah, so we should move on to the. Oh, sorry. And so these are some of the figures that I've taken from this paper. So they looked at the stress as a function of strain, and you see that this black. Yes, Srikant, I'll answer you at the end. And so if you look at the glass that is prepared at high temperature, at the initial temperature at 0.2, then you do not see any sharp overshoot in the stress versus strain. And this kind of yielding is more reminiscent of ductile yielding, which is represented in this panel B. And if you look at the stress strain curve for temperature 0.062, where you have a very sharp drop. So that is reminiscent of brittle-like failure, which manifests itself via shear band formation, depicted in this panel C. And this has been claimed to be a non-equilibrium first-order phase transition. And to support it, these authors also looked at the stress-strain curve as a function of increasing system size. And it seems that as you go to larger and larger system size, the drop becomes extremely sharp. And also they have computed susceptibility. Susceptibility seems to be increasing very rapidly and at the yielding point. So the take home of this work was that oil annealed system seems to yield via discontinuous brittle-like yielding process. And this is similar to what metallic glass and molecular glass does. And this yielding corresponds to probably a first order non-equilibrium phase transitions. And as you take slightly less annealed glasses, then this first order character becomes weak, and the transition terminates to a second order critical point, which has an universality class of Ising model in a random field. So this RFIM. And if you have a very poorly annealed glasses, then this transition becomes a smooth crossover, and which is reminiscent of rheological behavior of foams, gels, and colloids. So the point they tried to highlight, which is obtained by this Swap Monte Carlo method, is that these various forms of yielding process, brittle, quasi-brittle to ductile, has probably nothing to do with the material itself. It's probably related to their annealing history. So the really annealed glass will be always brittle-like, and quasi-brittle will be moderately annealed, and poor annealed glass is going to always show ductile behavior. And though these are questions that of interest to many, and a few further future research is definitely needed to understand whether indeed this is a first order non-equilibrium phase transitions. And in that context, Giorgio, Itamar, and Corrado and Murari, they looked at this yielding process using replica kind of calculations. So what they looked at, so if you take two configurations or call them replica, and they start from very similar structures. So they are basically have similar overlap, or maybe where overlap or Q is order parameter is close to 1. And then you shear them and then look at their how the overlap decays. And it seems that this overlap QAV, average of it, actually shows a very sharp decay at the yielding point. And this decay becomes even sharper if you take a larger and larger system size, telling that this replica order parameter is probably a correct, good order parameter to characterize the yielding transition in this kind of solids. And they also looked at the corresponding susceptibility. Susceptibility shows a large peak, and the peak increases with increasing system size, signaling a possible divergence with large system size. And so this tells that also yielding transition is probably some sort of a thermodynamic non-equilibrium transition. And it's associated with growing length scale with divergence, and it manifests itself by shear band formations. So this typical picture in the left-hand side is basically a line of SLBs, which is been associated as the origin for having a very clean shear band. Okay, so now so in the last 5 minutes, I come to this theory of swap accelerations. So this immense success of swap Monte Carlo actually inspired many to understand why this acceleration happens. And one of the theory which is suggested by group Matthew, Idan, and Carolina is that the swap Monte Carlo can be thought of as a minimization or a gradient descent process in an effective or effective potential. Okay, so this potential has two parts. One is the usual pairwise interactions, as well as there is a potential coming from size fluctuations. So size fluctuations here is taken as a kind of a harmonic kind of potentials. And if you take this effective potential and do a gradient minimization to generate the glass state, then you are going to get this ultra stable glasses. And indeed, this is what has been done in this physical review E work of Idan and Matthew, where they did this numerical work with this kind of potential, which allows the diameter of each particle to fluctuate within certain window, and the spring constant of the potential is varied. So this diagram tells you that for a spring constant of 10 to the 3, which is very large, the diameter fluctuation will be not very significant. Then you can get ultra stable glass just by doing quench in this effective potential. So this gives you a new method to generate ultra stable glasses and a new algorithm as well. Okay, so along with this, there is this controversy which came in, which is that this is work of Matthew and my case. So they said that as swap Monte Carlo destroys, speeds up the dynamics by a very, very large factor, and even at TG, the swap relaxation time is order of maybe 10 to the 3 to 10 to the 4. So probably there is no growing static length scale that controls glass transition, and the argument was that if a local move can remove all your barriers, so then those barriers are probably not thermodynamic in origin. So if they are not the thermodynamic barrier, then RA40 like theory and associated length scales are probably not the main player in understanding the physics of glass transitions. And then this is one big issue that appeared, and then this was addressed subsequently by Ludovic Giulio, Jean-Philippe Bousseau, and Gilles Tardieu, where they argued that even if you look at crystallization transition of this polydisperse systems, if you do normal Monte Carlo, this red time series denoted in the red color, so there you don't see crystallization. But if you introduce swap, then it crystallizes in roughly maybe 20 to 50 tau alpha time scale. And everybody knows this crystallization is surely associated with a thermodynamic energy barrier, which tells you that swap move can actually even nullify thermodynamic barriers to a large extent if the barriers are smaller in size. The question in the very large barrier limit, whether the Matthew Weir and Mike Cates argument still holds or not, is something which is open. But at this moment, it seems the swap acceleration does not rule out or disprove any type of theory, be it random first order transition theory or any dynamical theory like a facilitation theory of glasses. And I want to stop here saying that so this one swap algorithm and its subsequent development actually led to flurry of new understanding in the structural glass. And I really want to thank Giorgio for being one of the central player in this, and also to be an inspiration and role model for me, because he was my postdoc mentor. And once again, congratulations to him for this Nobel Prize, and thanks for your attention.
Thank you, Smarajit.
Stop here. Yeah. So.
Okay, thanks for a very nice talk. So Shrikant has been, he has his hand raised for a really long time.
Okay, Shrikant, yes.
Sorry, I thought Smarajit was winding up.
Yeah, I took a little more time.
I just wanted to be first in the queue. About the change in the character of yielding. Of course, everything that you described, I don't have any problem with, but just as a matter of record, normal MD simulations can reach temperatures across this the point at which the yielding becomes discontinuous. It's just that
this is what I should have added here actually.
Yeah.
No, but so in the enthusiasm of praising Swap too much, I actually moved into all of that. Sorry for it. Anyway, but I just wanted to highlight how impressive it was.
Yeah. No, it's fair to say that it made it easy to look at that phenomenology. So.
Yeah. Sure, yes.
Any other questions? Smarajit, I'll quickly ask you something. So you said, that increasing size polydispersity can fluidize a suspension. Yeah. So is there any calculation for any, given a certain, suspension? I mean, is there any calculation about a critical polydispersity value over which a suspension will never form a glass?
No, it's actually the other way around. Beyond critical polydispersity, you are always going to be in the glass phase if you are dense enough. And if it is below, this is 5% to 10%, then you get into crystal state.
Because if you have a huge distribution, then, of course, I'm talking about a real colloidal suspension. Then, if you have a wide distribution, then the tiny particles can always, they'll be more mobile because, they can always be, traveling within the gaps of the other particles. So for a very high polydispersity, shouldn't it fluidize?
Yeah, this is something which there are some work which suggest that for very high polydispersity, probably you will go into a state which are basically this fractionation, where you have various different crystals of different size. Or one part of it actually has one type of particle with the polydispersity goes down drastically.
Yeah, I understood that. I was just trying to reconcile that. Yeah.
Okay. So what I think, I don't know what is the current status. Maybe using the swap, one should actually look at some of this, whether this fractionation is an issue for very large polydispersity.
Okay, thank you. Thank you. BVR Tata ji has a question.
Yes, BVR, yes, Tata. We are not able to hear you.
Yeah, you are going from mute to unmute and then back again to mute.
Unmute.
Yes.
Unmute. Yes. Okay. Yes. Finally, I guess I'm okay. No, I have the same question like what Ranjani has asked. There are two possibilities, but in your paper, when you published in a PRL paper of a continuous form, you said it is a equilibrium state. Now, when you come to
using issue free energy functional, yes.
Yes. Now, there are also possibilities which when I published a paper, they also asked that, yes, if I have a continuous charge distribution of charge colloids, which are equivalent to continuous distribution of size colloids, then you can have a ordered state of small particles around a large particle, or vice versa. A large particle. So you can have a pockets of ordered states in the presence of the thing. So overall, you may have, like your pair correlation function shows some broadening, but there will be a local ordered states which will be there, which is like when we say nano short range ordered thing leading to an amorphous order.
So there will be local
this type of a state can be there. It is not truly a glass state, truly disordered state. Yeah.
So this is related to this medium range crystalline order, where size is of some small nanometer scale. Probably.
Yeah. So in a Fourier scale, you may see a peak at low Q. Yeah. Then my second question, just for a clarification, is the Swap Monte Carlo is essentially to take you out from the deep wells in the landscape picture?
Yes. This is exactly the reason. Yeah. So because these moves are non-local, so by doing this move, you are basically putting your system in a different part of the phase space immediately.
Then when I do in that case, if I do a mean square displacement versus Monte Carlo, do I see an accelerated acceleration which is unphysical?
Yeah,
because
you
of
see
this.
that. Yeah. You will see that mean square displacement is going to be very large.
Okay, fine. Thank you. Right. But a very nice talk. Lot of things. But you have you never told what is the disadvantage except what Srikanth has asked. You praised your Swap Monte Carlo.
No, there are many disadvantages as well. Yes. So there are one of them is like the missing time scale that you seriously miss, and then this is a puzzle of how to reliably estimate the time scale. To talk about the massive speed up, the massive speed up is only possible if you know what is the time scale that you are supposed to be at that. And all of this comes from extrapolation, which are a bit unphysical. Yeah, Srikanth and then Chandan.
Yes.
Okay. No, very quickly. I wasn't saying anything about disadvantages of swap, but about the earlier question of Ranjini, there is old theory that Peter Solich worked out some time ago, which
there's something by Emanuela Zaccarelli and Mike Cates, where they do an empty simulation and they actually show that if you increase the polydispersity, which is continuous, you actually get fluidization at the largest polydispersities. I'll send it to you.
In terms of equilibrium behavior, I think what Smarajit said is correct, that you expect, I mean, at least theoretically, you expect fractionation. And yeah.
Okay. Chandan?
Yes. The simulations that Ludovic and company have done, there are certain distributions, they actually see this fractionation. So they have to actually adjust the parameters of their distribution in such a way that over the time scales that they can access, they don't see fractionation. But in general, if you just have polydispersity, sort of the garden variety, then with this accelerated dynamics, you expect to see fractionation.
But I think if you look at this Ludovic's PRX paper in 2019 or something, they looked at binary, ternary, polydisperse of different varieties, including changing distributions, and they looked at across different temperatures. And in most of the cases, last few temperatures are basically crystal, going into crystalline mode. So basically, they are becoming polycrystal in most of the cases. So it is not very clear whether in any one occasion you can get a very good glass, which is going to survive under swap.
But at least they claim that for some cases they do see something that can be called a glass.
Yeah, but the window seems to be very restricted.
Yeah. So as I said, one has to tune parameters.
Parameters,
Yes. Yeah, that's all I wanted to say.
Okay. Thanks, Chandan. Shumilan?
Shumilan, unmute yourself and then...
Unmute.
Yeah, sorry. Can you hear me?
Loud. I cannot hear.
Sorry, there's some problem with my microphone. Can you hear me now?
It's better now.
Yeah, you can hear me now, yes.
Outing. So what I wanted to ask is this swap, if it is taking, let's say, from one inherent structure basin to other inherent structure basin, can you not estimate the time scale by some transition state theory, like going through some saddle points or something like that? I mean, associate some time scale with that move.
But then you need to know like the effective barrier between these two inherent structures. And that itself, calculating that barrier and the path that it can take will also be a big challenge, because you need to find out the lowest energy path along between these two minima, and then maybe you can do some sort of, this is true. But if it is not adjacent minima, then you are in a problem.
Right. No.
So that's why I think some of the local swap move may have some advantage. But these are all so random thoughts.
Right. Okay.
Okay, thanks.
Thanks. Thanks. I don't see any other raised hands at the moment. If there are any questions for the other two speakers in the session, Shrikant and Francesco are still here, so you can ask. If not, I think we'll just thank all the speakers and wind up for the day. Thank you. Thanks, everybody.